From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
The first and most important thing is this a good career path still, or is it mostly on its way out, right? I'd say it's absolutely a good career path to get into additive manufacturing. There are decades, many decades of good growth in this industry left. So that's always a consideration when I'm talking to somebody about their career trajectory. Like if they're young, does this career path have staying power for your whole career? And additive manufacturing, no doubt. We have many decades of amazing things ahead of us.
That was Brent Stucker. Brent is the Senior Vice President and Chief Scientist at 3D Systems. Prior to joining 3D Systems, Brent was a Distinguished Engineer and Director of Additive Manufacturing at Ansys, 3D Sim. The company Brent co-founded and led as CEO was acquired by Ansys in November 2017. Brent led the establishment of ASTM Int'l Committee F42 on Additive Manufacturing Technologies and its partnerships with ISO TC261, was the first chair from 2009 to 2014, and was elected to the ASTM International Board of Directors from 2015 to 2017. Brent has been a leading researcher in additive manufacturing for more than 25 years, with projects ranging from new materials development for biomedical implants and aerospace and defense structures to multi-scale modeling and control of AM machines. He was a professor from 1997 to 2015 with appointments at the University of Louisville, Utah State University, the University of Rhode Island, and VTT Technical Research Center in Finland. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcasts, including Spotify, Apple, Amazon, or Stitcher. Brent, it's a pleasure to have you on the podcast today. I'm excited for the conversation and kind of hearing your career story, because I think it's super impressive of all the different types of ways that you've worked with additive. So why don't we just jump in and start from the beginning? Kind of, I always start with like, where are you from originally, and what was kind of that first kind of tiptoe into either engineering or 3D printing? Where'd you get your start?
Yeah, well, thanks. Happy to be here, Mike. So I grew up in a little town in Idaho called Kuna, which at the time was very small and just surrounded by farms. Now it's a suburb of Boise, so it's all grown up around it. And went to University of Idaho as an undergraduate. That's the main research university in Idaho. And while there, joined ASME, American Society of Mechanical Engineers, and was reading in a mechanical engineering magazine, probably 1991, 1992. I don't know. I'd have to go back and see if I could even find the article. So that was, I guess, 30 years ago, 29 years ago, about this whole new area of rapid prototyping, stereolithography, FDM, laser sintering. Thought, that's kind of interesting. And then a year or so later, when I was heading to grad school, had a National Science Foundation graduate fellowship that basically let me go anywhere in the country, and it would pay for my tuition and fees and give me a stipend. So then I started looking around for great advisors then, since I could kind of go anywhere, and chose to go to Texas A&M and work with a guy there, Walter Bradley, who I really respected. And as we're talking about, what do you want to do for your PhD? I had a little bit more flexibility than most people. And I said, well, this area of rapid prototyping is really interesting to me. I've read a little bit about it, don't know much about it, but maybe we could build a PhD project out of that. And so that's how I got going. And then at that time, because it was so new, I could basically read everything that ever was published, because there wasn't very much that was published. And spent an entire summer before I went to grad school, basically going back and forth to a library, actually in West Virginia, which is where my current wife was living back when we were dating. She was living in West Virginia. So moved out there, lived so I could live close to her, and read everything I could find in various libraries at universities in West Virginia. And then did a tour of the whole northeastern United States to visit every single facility that I knew of had a rapid prototyping machine. So I visited Ford and GM and some little places with FDM machines and just a number of places. In fact, I found my little trip diary the other day as I was unpacking some old boxes of that trip I made in 1993. And out of that came some ideas for my PhD project. And that's kind of how I got started.
How did you find those people that had these machines?
I don't know. I'm assuming I found them from like the literature, because there wasn't the internet to search back then, right? So I have no. In fact, I wonder if I have those in my old notes, because it was tough to find people back then. You couldn't just search somebody on the internet. You couldn't. Which is how we'd all find people today, right? So how I found the actual people who were running the facilities and found their phone numbers and called them and set up these tours, I have no idea. But I saw, old Cubidol machines and laser centering machines, and some of the first Stratasys FDM machines and stereolithography machines, and got into some of these automotive factories. Actually, at this point, I can't even remember how I got myself in there. I guess it was just somehow sweet talked my way in to finding the right people. That's a great question. I haven't thought about that in years.
And did you always want to go down kind of the graduate school path? Was that kind of your intention as you started your university education?
No, in fact, I started out as a double majoring in mechanical and electrical engineering, because I thought, hey, if I had a major in both of those, I could really do just about anything. And did that for a couple of years. And after my sophomore year in college, actually had an interesting experience where I'm a Christian, and it felt like very clearly, actually through something that was supernatural, made me think I should be a professor. I felt like God was calling me to be a professor, and it totally just flipped my entire way of thinking about my future overnight, to be honest. And so then when I headed down the academic path, then that's when I decided to go get my PhD, and totally shifted everything down to that path. So but it was sort of happened the summer between my sophomore and junior year in college that kind of my whole life shifted at that point.
And after you did this tour of all these different facilities, what did you end up deciding to study for your thesis?
Yeah, so at the time, everything was new. So people were thinking, well, could we make tooling this way? Could we make real parts this way? And so one of the things that a bunch of people I talked to said, if we could print EDM electrodes, so EDM, electrical discharge machining, is how you make today, and back then made almost 100% of your injection molds, your die cast tooling. So you would form an electrode and you'd burn it into the metal to get the shape there for tooling. And so they said, hey, if we can make these electrodes with rapid prototyping, we could dramatically simplify the way we make tooling, and you could, burn that shape into any number of metals. And so the 4 years of my PhD work were spent, could we process the types of metals and ceramic composites? Well, first of all, I had to kind of look at the research and say, what could be built and what could potentially be a good EDM electrode. And so there was this unique material made up of zirconium diboride and copper that has some amazing electrode performance characteristics, but it's impossible to machine. So I ended up developing the whole science of how do you take using a binder on an SLS powder of ceramic, run it through a traditional SLS machine, form the green part, do the binder burnout, infiltrate with copper, all kinds of issues of chemistry, compatibility between copper and this alloy, and infiltrating it, and then all kinds of experiments having to do with using it as an electrode. So that was my PhD work, was a whole combination of the physics of EDM, the material characteristics that would make a good electrode, and then how to form a composite of that material using laser centering.
And as you're going through kind of the research, your thesis, and kind of writing and publishing, I guess, is there a different? So when I did my PhD, I probably it was like 99% sure that I wasn't going to go down the kind of professor track. So is there anything different that, like, as you kind of knew that the professor kind of was where you wanted to go, was like, there anything different that you would do where you like really focused on writing papers or kind of interfacing with companies or finding like, hey, where would I want to work? Or like, what was that like?
Yeah, that was, well, it was new to me because I was a first generation college student. So I went to college really without knowing anything about what academia was about. So as I learned about it, I think some of the core things, if you want to go down that academic path, certainly everybody knows you've got to learn to publish, right? Because it's like the publish or perish phrase is true. If you don't publish, you're not going to make it in academia. But what a lot of people don't recognize is to be a successful academic in engineering, you actually have to be an entrepreneur. You have to be able to start a research business. You have to sell your product to somebody, your product being, I'm going to mentor grad students. I'm going to create new knowledge that's going to move the world forward. Then you have to find somebody who will pay you to do that. And so you have to learn how to write proposals. Where can I go get money? How do I play that whole game? And so luckily, early on in my PhD, because I had funding for my actual stipend, I didn't have money for my research. So the first thing I did, even that first summer before I started my PhD, was start to work on proposals, and sent proposals to the National Science Foundation, and in fact got two funded, which then funded my whole PhD project. And so that was one aspect that was critically important, is to learn how to get money and how to run like an engineering business. How do I create a budget? How do I sell an idea? How do I then run the program? So that's I had a lot of freedom to do that as a grad student that most grad students don't get. So I feel really blessed from that. And the other thing I think in engineering is you've got to be connected to the practical. Like, what does industry really want? And so from the beginning, everything I did really closely with a group of interested companies, even in my PhD, to create what are the goals of what we're doing and really understand the market potential. And took that through my entire career. Every place I worked as a professor, would gather, create a center or some sort of, consortium of industry together with then pulling in a bunch of government money to help fund, new materials, new machines, new software, all these different things that I've researched over the years.
And where did you land after you finished the PhD?
Yeah, after my PhD, it was interesting. I had a really close relationship with DTM at the time, and they had provided the laser sintering machine to Texas A&M for my PhD work. And then they actually gave me a beta laser sintering machine to take with me to wherever I wanted to go, which is like crazy that they did that. So when I was applying for jobs, I had it in my cover letter, and I also have this very expensive piece of equipment that when I move, you go, and they had also promised $50,000 for a furnace wherever I went. So it was pretty amazing support I got from some of the people at DTM. It was actually Kevin McAuley there at the time who did that. And so that really put me on a unique path to be able to go straight to academia without a postdoc. I was in a brand new area, and if you want to go straight from PhD to be an assistant professor, the only way you can do that is if you're in a new area that they want to hire in, and there's not much. So it's a supply and demand problem, right? There wasn't much supply of people who knew anything about rapid prototyping, and there was some demand for it. So that, plus I had this equipment that got me a leg up to start immediately with a working lab, meant that I had quite a few offers. And so being a country boy at the time, I took the University of Rhode Island, which the university in Rhode Island is just in the middle of the countryside. It just had a great feel, had some really famous professors there that I got to work with. And so I started out working at University of Rhode Island for 5 years.
Yeah. And then as you kind of grew your research there, I'm assuming that's kind of like you're tracking with the kind of the growth of the industry as well, right? Like, yeah, AMUG is probably not AMUG yet. It's may not even been the 3D Systems user group yet, right? It's kind of
it wasn't. It was. We had an SLS users group that I was a part of, and then there was a stereolithography users group that was focused just on 3D Systems technology at the time. And then when 3D Systems bought DTM, we sort of merged those later on. But and behind my shoulder, you might be able to see the little, my little dinosaur there from the SLS users group that was, got, I don't know, a long time ago. So I've been a dinosaur so long, I'm now like fossilized to petroleum or something. So at the time it was, completely separate SLS users group, 3D Systems. I think it was 3D Systems North America Stereolithography Users Group. It was like this tiny little niche, which now today they merged and they grew into the industry-wide, AMUG, like you mentioned.
And so back at this time, you're kind of just starting your professorship. Like, are you like fully bought into rapid prototyping? You're like, hey, like this is going to change the world. Like, was there ever any doubt in your mind that like this is going to be an impactful technology?
There was never any doubt, because it was a game-changing, disruptive way of producing three-dimensional objects. So this whole concept of discretizing a three-dimensional object into 2D layers and then building them and stacking them, is just a disruptive way of creating geometry. And so to me, once you kind of bought into that vision that I can, discretize a 3D object and stack it up and build it, then to me, the rest of my career is about what's the applications, like what kind of new machine could I make that would process material in a new way? What's the energy sources? What's the layering methods that you could apply to this? And then what are the material systems that you could tweak or create from scratch that would be compatible with those energy and stacking sort of phenomena? And so I really bought into that as something that had legs and was going to be in the future. And I remember early on, just looking at the market size, which is pretty small for prototyping to start out with, but every little incremental improvement in software, machines, and materials opened up more market and more market and more market. And I could just see, hey, this has got legs for 20, 30, 50 years in the future. So I went all in on it and basically decided everything I'm going to do in academia is going to be based around some sort of angle on what back then we called rapid prototyping, or was starting to transition to rapid manufacturing a little bit, maybe in the late 90s, but still mostly rapid prototyping.
And how did that feed into what you were teaching, right? Because your research obviously is all rapid manufacturing, rapid prototyping, but would that come into your teaching as well in terms of your engineering courses or materials courses that you're doing?
Yeah, it did. And in fact, I mean, early on that meant, I kind of got assigned to teach what started out as like computer-aided manufacturing courses. Pretty soon thereafter, I proposed that we really should have a dedicated class for rapid prototyping. And I think in my first university, we did call it rapid prototyping. I think by the time I got to my second university, I called it additive manufacturing, but which is another story, how we came up with a standard, new terminology. Happy to talk about that. But so I proposed that dedicated class on that and started building up semester worth of information about, going through, and here's the various processes. So at that time, it was just all random information. There weren't really any good textbooks. There weren't even any good ways of subdividing this area of rapid prototyping into technology types. It was all, sort of trademarked machine names that various people had invented at that time. And it was a mess. And so that was a lot of my career, was bringing like order to that chaos. How do I present this whole area that's very chaotic in its nomenclature and in the way people think about it? And how do I bring order to that and teach students in a semester to go from nothing to where they could have a successful career in that industry and be able to navigate that? And that's actually been one of the great things that I don't know how many of my former students have worked in 3D printing, but it's in the hundreds, because I had so many of them. Even the first couple of times I taught a course, come back to me after they graduated and say, hey, I got this job specifically because of your class, because I could talk about the future of manufacturing and some technology that my company wanted to get into, and I already knew, what they should be interested in. So that was that was a major part of my teaching. And so I taught typically at most universities I would teach two courses as my primary thing. There would be additive manufacturing, there'd be material science. So I was never in a material science department. So I was always in mechanical or manufacturing or industrial engineering sort of departments. And so because of all my research was very material heavy, that was the other thing that I ended up teaching, was sort of a practical approach to material science.
So why don't we get into the nomenclature now? So you hinted a little bit at that, the shift towards additive manufacturing. What do you want to get into there?
So like late in my time, I think at University of Rhode Island, and then shifting into Utah State University, which is where I moved in 2002. I was thinking a lot about, how do we teach this stuff? So the Laser Institute of America had a handbook that they were coming out with, and they asked me to write a section in that handbook on this area of rapid prototyping. And so brought on this new postdoc, Janaki Ram from India, and we were just wrestling with how do we even make sense of all of these technologies. And we thought about some authors were separating machines by, well, if you deal with liquids, we'll call it a liquid machine, and if you deal with a powder, we'll call it a powder machine, and if you do with a solid, it's a solid machine. So the solids, they would put FDM in the same category as laminated sheets, or they would treat binder jetting as the same thing as laser sintering. Or if it was liquid, they would treat, stereolithography as the same as a melted wax printer. There's just, or they would say, oh no, we're categorized by whether it uses a single point of energy, so that we'll call one dimensional, or an array of energy, which we'll call a 2D machine. Or if we can use a DLP chip, we'll call it an array would be like 1.5D. And they had all these weird nomenclatures, and all of this was like, okay, I can see why you split up the industry this way, but it frankly is not helpful. It's like it doesn't really help people practically understand the difference between these technologies. And so working with Janaki Ram, we just spent a few months just brainstorming how do we make sense of this, because it made sense to us. Like in my own head, I would categorize similar technologies into a group, but how do I put it down in a way that makes sense to others? So one of the first things we did is say, what do we call this whole industry? And we chose to call it Additive Manufacturing Technologies. And I think looking back, that was really the first major thing that was printed using that nomenclature, was our handbook. And then that led to a textbook, which then was adopted, by ASTM when the basic approach of my textbook was adopted by ASTM when we started the ASTM Standards Committee. But, you go back a couple generations, the first version of this terminology set was this Laser Institute of America handbook that we published. And some of the unique things that we said, like I was trying to make sense of things like high-speed sintering, which was coming in research form, wasn't commercialized at the time, laser sintering, both the polymer and the metal. And so we came up, I just coined the term powderbed fusion as part of that conversation. You've got a powder bed, and people were arguing about sintering versus melting. Should we call it selective laser melting, selective laser sintering? Some people who were powder metal sinterers like that we called it sintering because we actually melted it. Like all of these silly arguments. So I'm like, okay, let's just avoid that whole argument, and let's just use the generic term fusion, and we'll try to short circuit people yelling at each other, in an academic sense, not in an actual yelling in reality, but so that's one term that just came up off the top of my head that is stuck in the industry now. And we call powder bed fusion a whole category of technology. And I would say about 60 to 70% of the terminology we created for that handbook was used in my textbook. And then about 80% of what was used in my textbook ended up getting adopted by ASTM. So it went through a couple iterations to where it is now, ASTM and ISO standards, and had great input, from Ian Gibson and David Rosen, who then were my co-authors on the textbook that we wrote together. And then again, when Terry Rollers was running the terminology subcommittee for our ASTM standards committee, he and I worked a lot on the terminology stuff. And I proposed basically the framework from our textbook, which with just a small amount of tweaking became the international standard for terminology.
Right. That's awesome. It's good to hear kind of the full history of how these terms kind of get originated, because you never think about it. Like someone had to decide somewhere that like it's Powderbed Fusion.
Yeah, exactly. And it was a combination of how do I make sense of this for the professionals that I'm writing to? And could I use this in class? Could I actually teach somebody who is completely new to this? Would this be helpful to them to have this categorization? And it was really wrestling back and forth with that for, a few months that came up with that.
And so I think I first met you probably after Utah State and when you were at University of Louisville. And so there, I think that was my first exposure. I was at Loughborough at the time, where in the US, I think you guys had to be one of the most prolific 3D printing organizations around, with all the consortium and the spinouts that you were doing as well. So kind of what was the transition there like, and kind of the growth of, is like the industry was really kicking up, you were there. So.
Yeah, I would say, the transition from Utah State to University of Louisville was really a big acceleration of my research. Worked closely with Tim Gornett and Tom Starr, who were there, had been there for a long time. In fact, I had known them from the 90s, and it was finally got to work together in the same team. It's a little ironic because back in '97, Louisville tried to recruit me at the same time Rhode Island was, and for some stories I don't need to go into, I chose to go to Rhode Island at the time. So
they give you the good bourbon.
13 years later to decide, okay, I am going to go there and work there, mostly because the leadership had changed substantially, and I felt like it was a much better atmosphere at that time to work in. But at Louisville, really, that was when metal laser sintering and E-beam was really taking off. This was just over 10 years ago, started there. So got some of the first EOS machines and RCAM machines. And I had been in metal, deposition since 98. I bought one of the very first Optimec machines. So I was really familiar with the physics of laser material interaction to deposit, fully molten solid material. But the Optimec machine, of course, is a metal deposition machine rather than a powder bed machine. And so it was not too much of a leap to move to direct metal laser sintering as a research area, because the physics and the sort of stuff I learned from working with the Optimec machine for so many years could directly translate. And of course, metal laser sintering gave you a lot of benefits for geometric complexity at the time. And so everybody was interested in metal laser sintering. And so that side of our research really took off, developing new alloys, new applications, increasing productivity of machines, comparing E-beam to metal laser sintering. And at the same time, I started a whole area of predictive simulation of these processes. How do they work? How are parts going to distort? How is the microstructure changing? And so that was going really, really well. And in 2013, really decided, that the software side was to the point where somebody should try to make this commercial. And, but we couldn't find anybody who really understood the potential of it. Like we tried to show, like, here's our papers. And they're like, well, we don't know what to do with that. Like, it's all theoretical stuff. Well, here's a little bit of code. Oh, we don't know what to do with it because that code is just a mess of PhD student, sort of code, right? Good code, but it's not commercially viable code in and of itself. And so we decided then, late 2013, to form a company, 3D Sim, and spin that out, and then kicked off operations of that in early 2014. but that was all while still being a professor, running my day-to-day operations, doing, interacting, sitting on, DARPA advisory committees and all this sort of stuff you do as a professor. So I was really split between two worlds of entrepreneurship and academia simultaneously. And it became overwhelming. Like I decided in 2015, I've just got to go one way or the other. Like I got to either let somebody take over the company or I've got to leave academia. And at the time I decided, well, I'm gonna give this a shot. I'll be an entrepreneur. I'll follow this, what was at that time just one narrow portion of all my research, which was the software side. So let's go see if we can make that work, because if predictive software becomes widely available and used, it's going to dramatically impact and benefit the industry. So I wound down my academic career and left in the summer of 2015.
So what kind of takeaways did you have from kind of your academic experience of kind of growing research teams and kind of securing funding, things like that? What was the biggest kind of takeaway that you then translated over to the entrepreneurship realm those early days when you're kind of first starting the company?
Yeah, one of the things that was surprising to me was how much running my research lab as a sort of an entrepreneurial enterprise was directly applicable to starting a real company. But the issue was that if you don't get the next research contract in academia, you still have courses, you still get paid, right? You just can't hire as many grad students and your research program slows down. In real life, as an entrepreneur, if you don't get the next contract, you may have to go bankrupt and fire everybody. And like the stress of the difference between those is substantial. But as a professor, some of the things that really helped me in my ability to be an entrepreneur is both of them have to sell the potential for the future, because you're raising money. And even as an entrepreneur, at least in the U.S. in high technology areas, you can get a lot of money from the government with SBIRs and other types of funding. And so all of that directly transferred from academia to entrepreneurship, where I still went and raised a ton of money from the government, in addition to from industry, in this case, industry are people actually investing in my company. But then when the product is in sort of an alpha stage, trying to sell them as an initial customer to pay for something that's, maybe only half baked, that's still what you do as a professor. You're always trying to find the early adopters who are willing to pay a premium to be the first one to try something. So that's true in academia. That's true in entrepreneurship. So there were a lot of synergies between being an engineering research professor and being a technology entrepreneur that really helped me a lot to keep the company afloat, actually.
And kind of, can you describe kind of the trajectory of the company? I mean, you guys it didn't take too long before you were acquired, right?
Yeah, we started early 2014. We were acquired in late 2017. Yeah. So, about 3.5 years. One of the things that's amazing is how much money it costs to build software. Like you think of software, it's just code, right? But one is the science side of it is so complex that a lot of the things we thought would work didn't work. So we had to keep trying and trying on the science side, on the finite element side, and all these algorithmic sides. Some of the things we proved at a small scale wouldn't scale up well to bigger phenomena and larger models and things like that. It mostly didn't scale up with speed as well as we thought it would. So then the predictions are too slow. So that's one side, is the whole science side. The other side is that if you want to build good software, you have to pay a lot of money to hire good software people. Good software people don't come cheap. And so we raised a lot of money and we spent a lot of money, and it went away way faster than we thought it would. So I always tell people it's going to take, 2 times as long and 2 times as much money, at least, if you're really lucky, or it's going to take 10 times as long and 10 times as much money as you thought. But it's never as easy either in time or money or difficulty as you think it will be when you set out to do it. And I think a lot of that is, as a professor, you'll only have to show proof of viability, and you can write a paper on it. And then you say the rest of this is left to some company to commercialize, right? And the student graduates and move on, right? And that's your PhD. Somebody got his PhD because they showed this new concept nobody else had showed before. You don't have to commercialize it. You don't have to get it to the 100%. Well, that last 20% is at least 80% of the work. And I didn't have a good appreciation for the difficulty of doing that last 20% when I was a professor.
Did you have, when you started out with the company, did you have a vision? Like, was this going to be something that you were always going to sell, or like kind of building it to sell to another organization, or kind of did you have any expectations early on of kind of where you wanted to take it?
I did. I mean, I really thought we wanted to grow it as its own standalone scientific, simulation entity that would start with additive manufacturing and then move to other types of technologies that have similar physics and expand as a standalone entity. And so that's one of the things that it was sort of a wake-up call, is the difficulty of doing that, particularly when you're working in this was a completely new type of product. No one was buying simulation of additive manufacturing software at the time. That didn't exist in the marketplace. And so we have, 20 something years of 3D printing history at the time, but nobody had ever used simulation to help them in their operations. Maybe in a deep research, portion of a company or something, or academia. So you're trying to create a market at the same time you're trying to sell something into that market. So like there was no market for simulation software. So it was a lot harder to create the market than I thought, and to convince people they needed it in the first place. And then once we had done a decent job of convincing the market that they needed it, all these other competitors sprung up really fast with, not the same kind of tool, but a tool that they claimed was helping in 3D printing. And so then you've got these companies with global sales and marketing organizations competing with a little startup that only has, like one dedicated salesperson and a part-time marketing person, right? And we realized that at the time, we realized we either need to go out and raise about $50 million to actually take this to market, or we need to sell to somebody who already owns a market and use their sales and marketing expertise to bring it to market. So I went through a whole process of trying to down select the correct direction, brought in an investment banker who ran a big process. We got offers for both types of models. Like, some people said, we'll invest in the company and we'll build it. Other people said, we'll buy you out and just integrate you. But in the end, by far the most compelling offers were to be bought out. And that also eliminated a ton of the stress of, bankruptcy, to be honest. Once you're part of a big organization that's profitable, they may eventually choose to de-emphasize that product or something, but you're part of something that, you're not worried about, my 20 employees and their 50 combined kids and spouses. And like, all of a sudden we have 70 people whose lives are kind of make or break on whether our company makes or break. That's a lot of weight to bear if you really care about your people, and carrying that weight was getting pretty tough. So that was part of why I chose to sell, just some of that security for the whole team, so that they had a future too.
Yeah. And you spent another 3-4 years at Ansys once?
Yeah, almost 4 years at Ansys, helping try to build that product line within Ansys before leaving.
Yeah. And speaking of that, so now you're at 3D Systems. And so what's your role there now?
Yeah, so I'm chief scientist at 3D Systems, which is a new role there. So we're sort of making the role up as we go. So just under 2 years ago, 3D Systems hired a new CEO, Jeff Graves, who was at MTS before that. He's, PhD material scientist and long ago, but has been in the business world for a long time. And he came into 3D Systems and really completely refocused 3D Systems back onto its historical roots of additive manufacturing. And also decided we're not going to compete with our customers, so we're going to sell off all of our service bureaus and be the solution provider. We're going to make machines and software and materials, and we're going to enable applications, and also a heavy focus on healthcare and biomedical applications. Producing surgical guides, implants, dentures, aligners, all of these things in the healthcare segment. And we're now getting into organ printing. Actually, not just getting into it, we've been in it a long time, and we're getting close to starting animal and human trials and organ printing and things like that. So 3D Systems is really focused in then on additive manufacturing and its applications in all industries. And there's bringing in a new set of technology leadership who've been in the industry for a while, because a lot of their senior people who had been in the industry for a while had left over time. And so I was brought in as part of trying to add more, I think, industry long-term technology expertise at the leadership level. And so my job then, having been around for almost 30 years and having worked in all kinds of areas of the industry, is to make sure that 3D Systems is at the forefront of each technology it's playing in. So make sure our machines, our material, our software are competitive and market leading. So that's a very sort of broad kind of charge, but I'm not in charge of the organizational aspects of it. I'm supposed to help with the technology aspects of it. So it's, how do we build the next generation machines? What are the technologies we should be looking at? Is there a university we should be partnering with? Is there a national lab we should be partnering with? Is there a company we should acquire because it has some game-changing technology that we want to integrate with some of our equipment? So those are the sort of things I'm doing on a day-to-day basis.
It's almost like combining all your previous experience, right? Kind of looking at all different facets.
Exactly. And that's why I took the job. I wasn't really looking for another position, but was recruited into this position and decided to do it because it is exactly that. It's instead of just this narrow area of software I've been working on for the last 6 years, it's basically said I can play in this bigger sandbox that I love to play in, which is new hardware, new software, of course, new materials, new applications. So really that opens back up that broader additive manufacturing ecosystem to say, hey, I can start to influence all of these areas again, which is really exciting to me.
And where do you see, is really kind of the medical space kind of the big growth area that you see for additive, or are other sectors really accelerating as well?
I think there's quite a few sectors accelerating. I mean, that's one of them. I think there's a lot of growth potential there. There is still lots of growth potential in the aerospace market. Right now, one of the hottest areas is what people sometimes call new space, meaning like the SpaceX, Blue Origin, Relativity Space. All of those guys are growing incredibly quickly. And if this new space turns into, more of a taking humans beyond, our planet on a regular basis, then, which is of course the dream of a number of these new space entrepreneurs, then that's going to, continue to grow substantially for the foreseeable future. But at the same time, traditional aerospace is really hot, and we're starting to see things like automotive, which has been something we've talked about going back to when I very first started in rapid prototyping, right? Automotive drove a lot of the prototyping applications, and has always been what people have hoped to someday be able to produce end-use components at scale for automotive. And we are finally starting to see that on the horizon after 30 years, where we can say, hey, machines are getting fast enough, materials are getting good enough that we are going to start printing, real automotive components at production scale. I mean, of course, we've been printing automotive components for pre-production or for low volume production scales for many years. There's lots of little examples of that, but not printing, production parts for something that's, a really popular model of an automobile, for instance. We've just never been able to compete at scale for that. And I think we're almost there. And that, of course, if we can do that, we can do any number of other applications, right?
Absolutely. And so as we wind down the conversation, I mean, you've had such a wide ranging career with a lot of amazing companies and experiences. Like, for someone that's just starting out or looking to make a career change and it's already in manufacturing, maybe, like, do you have a piece of advice that you could share from your experiences?
Yeah. The first and most important thing is this a good career path still, or is it mostly on its way out, right? I'd say it's absolutely a good career path to get into additive manufacturing. There are many decades of good growth in this industry left. So that's always a consideration when I'm talking to somebody about their career trajectory. Like, if they're young, does this career path have staying power for your whole career? And additive manufacturing, no doubt, we have many decades of amazing things ahead of us. Then the second thing is, okay, what do I do to then differentiate myself within this industry? And I tell people, become an expert in something. I don't really care what it is, but find something that interests you within this area and get in and be the go-to person for that area in your company, but in the industry. And then really start getting out there and being connected in the industry. Like, go to AMUG, go to Rapid, go to FormNext. If you're part of some other society, that's some niche, SAE or whatever, Materials Research Society, or whatever your angle is in additive. Yeah, of course, go and do those societies too. But get involved in the additive community. If you're happy just to kind of sit at home wherever you live and not be involved, then that's fine too. You can have a good career. But if you really want to be connected to the international community and really find, I think, a lot of the fun that can come from being part of almost like a movement of changing the world through additive manufacturing, then you got to go to the trade shows and the conferences and get to know people and get to know, sit down over a meal and just talk about what are you doing, and then look for opportunities to get involved in things like standards. Anybody, even a young person in a company, can get involved in a standards committee. It'll open your eyes to the world and help you look at things in a new way. So don't forget about those opportunities. It's very good for your career and just for keeping your brain thinking about broader issues related to what you do.
Fantastic. Well, thank you so much for your time today. Look forward to seeing you at some of these upcoming trade shows.
Thanks, Mike.
Perfect.